Hi guys. So today we are going to take what we've learned so far about exponential growth and decay and just look at a lot of applications of those. So we're going to start off with our basic exponential growth and decay models here. This is how we rewrote those expressions last class. So remember, if it's going to be a number greater than 1 here in the parentheses, it's going to show growth. If it's a number less than 1, then it's going to show decay. So the first one, it goes ahead and gives us the equation. So we're going to determine what these values mean. It says the value of a car in thousands of dollars can be approximated by the model y equals 31 times 0.92 to the t. T is the number of years since the car was new. So the first thing we're going to do is determine if this is growth or decay, and this is decay because that value right there of the base is less than 1. So the factor would be that 0.92. It would be at 0.92 times each time basically to figure out how much it's decaying. The percent increase or decrease, though, remember, is going to be 1 minus 0.08. So that would be an 8% decrease there. So we want to estimate the value, when the value of the car would be $9,600. So what we're going to do, we are going to learn how to solve these algebraically, but we have not figured that out yet because we don't know logs. So for this part of the unit, we're really going to use a calculator to help us solve these equations. So today is going to be really dependent on some calculator usage. So what we want to do is we want to estimate when the value of the car is going to be $9,600. So what I'm going to do is I'm going to take my equation, and there's a couple different ways that we can solve this. But what I'm going to do is I'm going to go ahead and graph this. So I'm going to go to my calculator. I'm going to go ahead and graph this model. Then what I'm going to do after I graph it, we're going to go to gsolve, and we're going to look at the function that is xcal. So if you remember when you do gsolve, you'll see an xcal and a ycal option. What that does, if you do xcal, it's going to pop up a box that says y equals. Well, we want to know what our x value is when y equals a certain value. Now, I do want you to be careful here. You may be tempted to say when y equals 9,600. That doesn't actually make sense for the model that we're given, though, because it says that this model is based off of the value of the car in thousands of dollars. That's why there's a 31 here as the initial amount. This car did not cost $31 when we bought it. This car cost $31,000 when we bought it. So we're not going to use 9,600 as the y value. We're going to use 9.6 because that's how many thousands of dollars we're actually looking at. So I'm going to go ahead and pull up my calculator, but again, let's just look at this real quick. We're going to plug in our equation into y equals. We're going to graph it, and then we're going to go to xcal and do 9.6. All right, so I've got my calculator here. So here's my equation plugged in. I'm going to go ahead and graph this. All right, so I already have a kind of a decent window set up. Again, if you're not sure about that window, you can zoom in, zoom out. What we also can do, though, I'm going to go ahead and actually set my window just for a little bit of practice. So I'm going to do F3. And let's just think about what makes sense for this problem here. X stands for time. All right, so I don't care about negative time, so I'm going to make that 0. Y is going to be the price of our car. Well, we don't really care about a negative car value, so I'll make that 0. And the Y max is the maximum value here. Well, we know we bought this car for $31,000, so that's about the biggest max we're going to have. And that's going to give us a really accurate window where we can see a lot of this graph. All right, so in order to figure out that value, we're going to go to gsolve. And I don't see that option currently, so I'm going to do F6. And then, again, we are looking for an x value, so I'm going to do xcal. The y value that we're plugging in is 9.6. And that's going to give me my answer of 14 years. So 14 years after we bought it, that car will be worth $9,600. All right, so let's look at another one. This time we're going to write the equation. So in 2000, the population of a city was 1.04 million. During the next 14 years, the population increased 2.05% each year. So to write this equation, since it's increasing, A is our initial amount. So the initial amount here was 1.04 million. We are talking about growth. It's increasing, so it'll be 1 plus 0.0205. Again, we write it as a decimal. And that's going to be to the t, or x. So we want to estimate the city's population in 2008. So we want to know what y is when x is 2008. So there's two ways we can do this. One is you can just go to run matrix and fill in that x value, right? We want to know in 2008, that is an x value of 8. So go ahead and plug in 8 for x, type that into run matrix. The other option, leave it here, plug it into your graph, and then you could do y cal. So, whoops, sorry. Yes, y cal. And then you could do x equals h. Either of those options would work. I would probably just plug it into run matrix because I think that's a little bit simpler. One thing just to be careful of though, if you do replace this with h, you don't want to plug that into your graph because it's just going to give you a straight line. Now, if you understand that straight line is your answer, you can do that. But remember, when 8 is there, we don't actually have a function here. We just have a value, okay? That's why this would just be something you would just plug into run matrix to actually get what that decimal is. And let me get a calculator. And that decimal would be about 1.22 million. All right, so for the next one, this one we do want to go ahead and graph. So let's graph our function, 1.04 times 1.0205 to the x. We want to know the year that the population was 1.3 million. So we'll go to xcal and do y equals 1.3. All right, so there's my equation. Now, if I just use that previous previous window I had, it's probably not the best. So some ways we can make this better. Let's go to your window, which is F3. I'm okay with my X max, I think. I want to make my Y max a lot smaller. I don't think this town that was at 1 million is going to end up at 31 million for a very long time. So I'm going to go ahead and make that just down to 10 to make this just a little bit easier to see. And now we can see that. Now, again, if you kept it there, it would be fine. But I'm just making it a little bit smaller to see a little bit more of that growth. All right, so again, here we're doing, we want to do an xcal, so gsolve, F5, F6 to see more options, and we'll do a ycal. The x value that we're plugging, the x value I did backwards, so sorry guys. There we go. Xcal, y equals, I want a y value of 1.3. Which tells me it's about 11 years. Now, again, it's 11 years after the original. So 11 years after 2000. So in 2011 is about when that population is going to be 1.3 million. All right, so we're going to look at a couple more growth and decay situations. The next one we're going to look at is half-life. So this is something you may have already talked about in chemistry. Half-life is what it sounds like. It's how long it takes for something to decrease by half. So if you think about it here, that growth or decay factor here is 1/2. Okay, every time it's decaying by 1/2. But what we're going to consider is there's a certain period of time it takes for that to happen. So let's look at this first one. It says the half-life of a radioactive element is 20 days. That means after every 20 days, we're going to have half as much. So if I started with 100 grams of it, okay, after 20 days, there'd be 50. After 40 days, there'd be 25. After 60 days, there'd be 12.5, and so on and so forth, exactly at those intervals of 20. Now, the problem here, though, is, well, we don't really necessarily care about 20 days. What if I want to know what happens at 25 days? That's why I want to use this half-life equation here to be able to figure out the answer to that. So this half-life equation, it's exactly like that growth and decay equation we just did. The only difference is instead of 1 minus that 0.5, okay, because, again, we know it's decreasing by half, we already go ahead and put the half in there. But you'll also notice here, up here in the exponent, there's that fraction. That's because the time that it takes, we're considering how many of those halving periods we're going to have. Well, if every 20 days that's going to happen, then we're going to take whatever our time is and divide it by 20. So that h, that is whatever your half-life actually is. So let's look at this first one. It says you start with 1,000 grams. How many grams would remain after 1 year? Well, we need to make sure we keep our time consistent. So we need to make sure we consider that this is 365 days. So if I plug this into my equation, 1,000 is the original amount. It's cutting in half. The time that it would take is 365, but we're going to divide that by 20 because that's what the half-life is. That's how many of those doubling or halving periods we're actually going to get. So we want to know how much we'd have. At this point, you can just plug this straight into a calculator and run matrix, and you would get your answer. We would end up with about 0.0032 grams. So a similar formula but the opposite reaction here is doubling growth. So if something doubles every set number of hours or days, etc., we can use a very similar equation just with a 2. Or tripling or quadrupling. As long as it's consistent over a period of time, we can use a very similar formula to this. So this next one, we have the number of bacteria doubling every 4 hours. There are initially 30 bacteria. Approximately how many hours will there be 300 bacteria? So let's set up our equation. The initial amount here, there were initially 30. It's doubling. It's doubling every 4 hours. So we don't know how many, but we know that the doubling period is 4. So we divide it by 4. We want to know when there will be 300. So this is a case where we're going to graph this. So we want to do an xcal when y is equal to 300. So we can go ahead and graph that function. All right, so I have my function graphed, or my equation typed in. We'll plug that in. Again, I'm probably not going to see a very good picture here, so let me go ahead and adjust my window. My x's, I'll go ahead and make my x's a little bit smaller, just to make that a little bit better. There we go. Okay, and then our x max is going to need to be a lot larger than that, because we started with 30, so it definitely needs to be bigger than 10. And if it's going to double every 4 hours, it's going to double for a while. And again, we're trying to find when there's 300. So if that's the case, I need my y max to be at least 300. So we'll make it 350. All right, now let's go ahead and graph it. And that's a much better picture of our graph. All right, so again, let's go gsolve, F6. We're doing an xcal. I want to know when y is equal to 300. And I get about 13.28 hours. So again, your time here is going to be consistent. Whatever the time was in the original problem, that's the time that we're going to keep it. So the original problem was hours, so the answer that we got was in relation to hours. All right, so the last type of application we're going to look at is compound interest. So the first thing I want to show you guys is just what it means for interest to compound. Interest compounds basically when it's added into your account. So the more often it's compounded, the more money you're going to have, because your interest then is going to be gained off of interest. So to show you a real basic example of kind of how this works, I want to show you the difference between interest compounded yearly and quarterly. So if interest is compounded yearly, what that means is, let's say you start with $100. You get 10% annual interest. Okay, you're probably not going to be able to find 10% interest on $100, but you never know. If you did that, okay, at the end of your first year, you start off that first year with 100, you get 10% interest, which would be $10. At the end of the year, you have $110. Well, now you're going into year 2 with $110. So year 2, when you get your 10% interest, you're going to get $11. So now at the end of that year, you're going to have $121. Well, now you go into year 3, you're starting with $121. Your interest now is going to be $12.10. So if you notice now, each year you're getting more interest without actually doing anything, because that interest is being added back into your account and increasing the amount of money that you have. So now let's look at what happens if that interest was compounded quarterly, so every 3 months. So let's look at the first quarter. So we're still going to take that $100. You're still going to get 10% interest, which is $10. But it's not the end of the year yet, so you're only going to get a fourth of that interest, which in this case is going to be $2.50. So at the end of the first quarter, you have $102.50. Well, now let's start the second quarter. You've got $102.50. You are still going to get your 10% interest. But you're only going to get a quarter of that interest because it's only a quarter of the year. So at the end of that quarter, you have $105.06. So we're starting the third quarter. So now we're in, I guess, July at this point. So you've got $105.06. You're still going to get that 10%, which is now $10.51. You're only going to get a quarter of it, though. You're at $107.69 at the end of the third quarter, which would be now putting us at about October, so beginning of October. So we've got $107.69. We're going to get that quarter of the interest, which is $10.77. Add that in, and now we have $110.38. Well, the end of the fourth quarter, that is the end of year 1. So if you see, if it's compounded yearly, you only have $110. However, if it's compounded quarterly, we have $110 and an extra 38 cents. So it may not seem like a lot, but it does make a difference how often it's compounded. Now, if you have a lot of money, a high interest rate in a long time, it could actually make a decent impact. So just always consider the amount that interest is compounded whenever you're considering these financial things. So here is our compound interest formula. So a couple of things that are on here. R is rate. Rate is always needs to be written as a decimal. Okay, so if it's 5%, it's 0.05. N is the number of times it's compounded a year. So that's in the equation twice. So if you think about it up here, the reason those are multiplied, that gives you the compounding periods. Okay, T is your time. It's always time in years. And then P is your principal, which is your starting amount. So let's go ahead and look at some examples using this equation. So you're deciding between two accounts. One pays 1.65% annual interest that is compounded daily. The other is 1.68% annual interest and it's compounded quarterly. We want to see which account is going to have more after 5 years. So let's look at both of these setups. So the first one, we've got $10,000 and we're going to plug those numbers into that equation. So 1 plus the rate as a decimal, 0.0165. divided by the number of times it's compounded. So 1.65% was compounded daily. That's 365. The same 365 goes up there, and we're looking at 5 years. So times 5. All right, let's go ahead and look at setup number 2. It's still $10,000 to start. The interest rate here, though, is that looks like an H. 0.0168. And then we're going to divide that by, it's compounded quarterly. So we'll do 4. The same 4 goes up here. And again, we're looking at 5 years. So since our variable is already by itself, we can go ahead and plug these into run matrix. Just go ahead and type them in the way they are. And we'll see which one gives us more money. So option 1, even though it's compounded more frequently, that's $10,859.97. Option number 2, it's going to be $10,874.38. So even though the first one was compounded more frequently, the bigger interest rate made a bigger difference and gave us more money. Okay, so again, compounding is something to consider, but a lot of times that bigger interest rate can make a bigger difference. All right, so there is one last formula that we need to consider. This is frequently referred to as the Pert Formula because it looks like it says the word Pert. And that is for continuously compounded interest. So a different type of compounding for interest, we can look at daily, weekly, monthly, yearly. But there is a type of interest that's called continuous. And that just basically means, think about it if it's every second, that interest upon interest upon interest. Now, it seems like it'd be a lot of money, just exponentially big. But because you're doing those decimals on decimals on decimals on decimals, it is going to eventually kind of bottom out to where you're not going to see just an infinite amount of interest. So no, it sounds like a crazy amount, but it's not going to be a significantly much larger difference than if it's compounded daily, weekly, monthly, yearly, etc. Now, it is going to be more, but it's not going to be a crazy amount more. The way we're going to use this formula is we're going to use E, that we talked about last class, that Euler's number E. Now, if you remember, the formula that we use actually to be able to calculate E actually is very similar to that compound interest formula. So that's why it kind of looks like a little bit similar here. So in this formula, P is your principal, that's your starting amount. E is the Euler's number E, that 2.718 number. R is your rate as a decimal, and T again is time in years. So let's look at this one. We have $5,000 to invest in an account that earns 1.75% annual interest compounded continuously. So if you see the phrase compounded continuously, you will use this Pert formula. If you see the phrase compounded any other period of time, you're going to use the formula that we used in the previous example. Right? But compounded continuously, that specific phrase means we're going to use the Pert formula. So we want to know how much money we'll have in 10 years. So let's take our principal, which is $5,000. E is E. My rate as a decimal is 0.0175. And we want to know after 10 years. So this is something we can just plug into run matrix. So I'll go ahead and plug this one in so you guys can see where that E value is. All right, so here's 5,000. So E, if you do shift, and where it says LN, it looks like IN, it's actually an LN. That is where you're going to find the E. It does automatically give you a decimal, but we can go ahead and plug that in then, and we've got 0.0175, and we want to know after 10 years. And that's going to tell us we'll have $5,956.23. Question number 2, wanted to know when we would have $7,000 in the account. So this is a case where we need to graph it. So we'll go to our graph. We'll type in our equation. So 5,000 e to the 0.0175x. So once we have this typed in, we're going to graph it. We're probably going to need to adjust our window. So F3 for our window. I'll keep my x's about right. Hopefully it'll be within 25 years. I can make a bigger x if I need to. My y's, though, let's think about this. We're starting with $5,000. Okay, so this y max is going to need to be at least $5,000. And we want to know when we have 7,000. So I need it to be at least 7,000. I'll go ahead and just make it 10 so I can see a little bit more. And there's my graph. We want to know when there's 7,000. So we're looking for an x, so we're going to do an xcal. So gsolve, F6, xcal. So I want to know when y is 7,000. And that tells me it's going to take about 19 years to have $7,000. All right, let's look at our last example. Baker Bank offers an account with 3% interest compounded continuously. Treese Bank offers an account with 2% interest compounded quarterly. So Judah is going to deposit $5,000 in Baker Bank. So let's look at what Judah's going to do. So he is going to put $5,000 in an account that is compounded continuously. So we're going to use the Pert formula. So e to the 0.03x. Jordan is going to put his money into Treese Bank. So he also has $5,000. It is compounded quarterly with 2% interest. So it doesn't really sound like a good deal. It sounds like Judah's going to be making a little bit more money, but that's okay. He's older. He's wiser. So that would be my equation for Jordan. So what this question's asking for, this is asking for when will Judah have $500 more than Jordan? Now we know Judah's going to have more money, okay? He has a bigger interest rate. It's compounding more frequently. He's clearly going to have more money. We want to know specifically the when he'll have $5,000 more. So probably the easiest way to do this is, again, to do this by graphing. But I don't want to just graph these two equations because it'd be pretty hard then to kind of guess and check and figure out when it's going to be exactly $500 more. So what I can do then is I can figure out when these two equations are equal with one of them having $500 more than the other. So what I'm going to do is I'm going to graph Judah as y1. I'm going to graph Jordan as y2. But since I want to know when Judah has $500 more, let's go ahead and give Jordan that extra $500 and see when they're equal. So I'm going to go ahead and graph these two things. Since I gave Jordan that extra $500 boost, we can then find the intersection. All right, so I have my two equations here. Again, the second equation, I went ahead and put that plus 500 on it because I want to know when they're equal, when this one will be $500 more. Now, if you flipped that, you probably wouldn't be able to find that intersection in a positive value. So that would give you a clue that you might have them backwards. All right, so now we can see our two graphs. And I'm going to intersect. So gsolve intersection. So they are going to have the same amount based off these equations after 8 years. So after 8 years, Judah will have exactly $500 more than Jordan. All right, so that is it for applications for today. Again, just keep in mind when to use which of these equations, especially in your interest. Make sure you pay attention to when it's compounded. If it's compounded continuously, we need to use that Pert formula.